Well, welcome back. Here we are on part C, and this is the part where you're going to see that not everything on chemistry is clear cut, and that sometimes you get partial truth while you're learning chemistry. So on this part, we're gonna learn about substances that do not contain hydrogen and behave like acids. Because on 1411, I told you, or you learned, that to be an acid, you need to have a hydrogen that you can release or donate, right? So let's look at these substances. So we're going to be talking about salts. And salts are nothing more than ionic compounds. Traditionally, we call sodium chloride salt. And that's just because it is an ionic compound, a metal with a non-metal. So how come salts can behave like acids? Well, let's see. We know we can dissolve most of the ionic compounds based on the solubility table. We know we can dissolve them in water. So let's see how we go from solubility to acidity. So we're going to be evaluating the acid-base behavior of salts. That's what we're doing on this part. And let's begin with this problem. Determine if each salt will form a solution, so it's dissolving, that is acidic, basic, or pH neutral. So let's find out. So if it's acidic, it's because we increase the concentration of hydronium. If it's basic, it's because we increase the concentration of hydroxide, or up to a point we can decrease the concentration of hydronium. If it's neutral, nothing happens. So the way we're gonna do that is we're gonna take the salt in question, and when we put this in water, it's gonna dissolve, and it's gonna give us iron 3 on this case, based on the formula, right? And chloride. We know it's 3 of them, but all we care is that we're getting chloride. And then this is what we do. The moment the chloride went into the water, notice that the chloride is negative, right? So negative will be looking for positive, secret of life, positive love negative. So this negative is looking for a proton. So it's gonna act like a base. It's attracting a proton to make ACl. So when that happens, chloride behaves like a base, so it accepts a proton and it becomes neutral, and water loses a proton, becoming hydroxide. So that's really easy. It's a single displacement reaction, basically. But it's a neutralization because it's an acid and a base. But you're not done yet. Now you have to say, okay, what did I produce? I produce a strong acid. Remember, you need to know those 7 strong acids. So I produce a strong acid, so strong acids will break apart. And they are strong acids because they are not going to form an equilibrium. So there's no equilibrium, so that cannot happen. So when you put chloride in water, chloride is such a weak base. How do I know chloride is a weak base? Because the conjugate acid is a strong acid. Conjugate bases of strong acids are very weak bases. So this is not going to be able to take the hydrogen, so this reaction doesn't happen. So the water, which is pH equals 7, the water is not affected. So the chloride causes pH neutral. But we're not done with the story. What about the iron? So let me clear the screen. So we know the chloride is irrelevant. The chloride is not going to do anything to the water because it forms a strong acid, and it cannot form a strong acid. The strong acid is going to break and it's not going to be an equilibrium. So there's no reaction of C chloride with water as a base. What about the iron? Well, the iron is a different story. This iron, which is very positive, would love to combine with something like that, something with electrons to give off. So let me show you what happens here. This is the iron, and the water. So you got the iron with an empty orbital, probably two empty orbitals, it's 3 plus, right? And now you have the water. And what do we know about the water? The water has two lone pairs, so you need to know your Lewis structure, right? So this is gonna be donated there. So this is actually, we call the iron and most of the metals, this is a Lewis acid. So a new definition. A Lewis acid is a substance that accepts lone pairs. So a substance that can take lone pairs is a Lewis acid. So this is my iron. It takes the lone pair of this water molecule. It takes the lone pair of this water molecule. It actually can accommodate 6 of them. Overall, it's still gonna be 3 plus. And we're gonna talk about, that's what we call a complex. We're gonna talk about that on chapter 18. So for right now, just know that the lone pair is going into the acid. So why do we call that a Lewis acid? Why acid? Why Lewis acid? Well, the moment these lone pairs go toward the acid, this develops, not really, but imagine that it develops a partially positive charge, which means it's going to attract the electrons on these bonds. It's trying to replenish itself, which what it's doing is attracting the electrons toward it, making the hydrogen be hanging there by a thread. That's the way I like to see it. The electronic density on the hydrogen is very, very small, which means this positive neutron, this positive nucleus, sorry, this positive nucleus is very exposed, almost naked from electron because the electrons are being attracted this way. Because of that, when you get another molecule of water close by, which is a strong polar molecule, a dipole, it's gonna sense that nucleus really, really strong, and it's gonna break it apart, therefore creating hydronium. So the meta on the traditional definition of an acid being able to donate protons or being able to produce hydronium, it cannot donate protons, so it's definitely not going to behave like a Bronsted-Lowry acid, but it's going to increase the amount of hydronium in the water by virtue of having a very weak oxygen and hydrogen bond. So that's what we are seeing here. This bond is very weak. So these lone pairs here take it and break that bond, therefore creating hydronium. So whenever you have a metal, especially a transition metal, that's going to happen. So you gotta be able to say, okay, so very simplified way, we saw that there's like 6 water molecules, right? On a very simplified way, this is gonna react with water, and in the process, it's not a balance equation, it's gonna produce hydronium. So this dissolving in water is gonna make the solution acidic because it's increasing the concentration of hydronium. So that's how we approach that. Are we creating a strong acid? Yes, so that cannot happen. Do we have a Lewis acid involved, like a metal, a positive metal? Yes, so that's gonna make it acidic. So let's do the next one. Sodium fluoride. So we're gonna have Na plus, and we're gonna have F negative, right? Both of them are gonna react with water. Once they dissolve, now they are in the water, so the sodium react with water, producing NaOH, releasing the hydrogen. So this is a Lewis acid. So in a very simplified way, right? It's going to create sodium hydroxide and hydronium. So that should make it acidic. However, the same way you learn the strong acids from 1411, remember the strong bases. The strong bases, first thing, they're going to be ionic. Second, they have to contain hydroxide. And third, the metal has to be from group 1, the alkali metals, or group 2, the alkali earth metal, except beryllium and magnesium. So any sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, calcium hydroxide, all of those are going to be strong bases. So strong bases are going to be halide bases. So they're going to break apart. They are strong bases, so they're not going to make an equilibrium. So that means the formation of this cannot happen because it's always breaking apart. So this is going to be pH neutral. That's not going to affect the water. What about the fluoride? Well, the fluoride is going to combine with the H from the water. F negative is a base, and it's going to produce OH negative. And according to the Arrhenius definition, anything that increases the concentration of hydroxide is a base. Well, let's look at this. We just created the conjugate acid is a weak acid. Therefore, it's going to establish an equilibrium, which means this will happen. And since this is creating OH, it's going to make the solution basic. So let's do one more, and I let you practice with the other ones on your own. Let's do this one because it looks weird. So C6, H5, NH3, NO2. We're only gonna split this into two sections, so don't try to go crazy and split it in a bunch of places. Look for stuff that you recognize for sure. We recognize ammonia, but that means we will have to split it in 3 parts, so we're not gonna do that. Or we can recognize a polyatomic ion, nitrite. So this is gonna be NO2 negative and C6, H5, NH3 plus, right? Because it has to balance. So if we combine this with water, it's negative, so it wants to get a proton. So that's going to give you H and O and OH negative, which will make this basic. Only if this is possible. So this is nitrous acid, which is a weak acid. Therefore, it will establish an equilibrium. So that means this will happen. If we can establish an equilibrium, that will happen. So it's gonna, therefore, that by itself is gonna make the solution basic. What about the other part? The other part is positive. So that means it wants to lose a positive to be stable. So when you combine it with water, the conjugate base, this is the acid because it's going to lose a proton. The conjugate base is going to be stable because it's going to be neutral now. And that proton is going to go to the water, increasing the hydronium concentration. So So because it's increasing because it's forming hydronium, this is gonna be acidic. Only if this can be made. If these are strong, so this is the acid, so this was the acid, right? So this has to be the conjugate base. Is this one of the strong bases? No, strong bases have to contain a metal and hydroxide. And the metal has to be from families 1 or family 2, except beryllium and magnesium. So this will happen, and it creates an equilibrium. So this will happen. So this is a conundrum. It's making the solution basic at the same time that it's making the solution acidic. So which one predominates? Well, what you're going to have to do, you're going to have to go to a table and find that and find how much is the KB of this. You need to find the KB on a table or the internet. And you need to find the KB for that one also. Actually, sorry. So this will be a Ka, right? Because it's behaving like an acid. Sorry for that. And then you're gonna have to see the Kb of the Kb of one versus the Ka of the other one. Which one wins? If Ka is bigger than Kb, then it's acidic. If Kb happens to be bigger than Ka, then it would be basic because it predominates. So that's how we do that. So make sure you practice this. At first, appears to be very complicated. It's not really that complicated. So go to the book, read it at your own pace, and you will see, as long as you are good identifying the strong acids and strong bases, as long as you can recognize an equilibrium, as long as you are already comfortable dealing with Kas and Kbs from from the beginning of the chapter, you should be able to understand this. If not, make sure you look at the tutorial videos posted on Canvas. So that's your daily work. And remember to look at the other two that I didn't do to get more familiar with them. And you're gonna need the solubility table, right? And you're gonna need to master your polyatomic ions also. And with that, we have covered the behaviors of salts when they dissolve in water and how they affect the pH of the water. In other words, how they behave as acids or bases. And with that, we will continue talking about acid and bases when we come back on our next to last section. So see you later. Take care.